Okay, so welcome back, everybody. Yesterday we ended with an example, or rather the beginning of an example, where we had computed the following thing. So just a reminder, we wanted to translate a point in 2D, and we noticed, the first thing before we even started on this process, we noticed that translation itself is like a very not linear thing, specifically because it moves the origin. And if we want our transformation to be represented as matrix multiplication, right? If we want our transformation to be done by matrix multiplication does not move the origin, right? Like at the heart of all of this, right? Yes, we proved this in the abstract vector space sense, but I mean even more directly if, let me pick a different pin here. If we have ooh, this one's bad too. If we have a function that we are defining as, or we are hoping is achievable via matrix multiplication. So there is some matrix A such that whatever this function does, it's really just multiplication on the left by A. Necessarily because of how matrix multiplication works, this is what we would have to get, right? It's not allowed to move the origin, okay? But translation very much moves the origin. So how do I deal with this if I still want a matrix? If I still want it to be, represented by matrix multiplication, or if I still want it to be matrix multiplication, and the trick that we did yesterday was instead of writing this as we normally would as column vector xy, we add this extra slot here. We put a 1 in this slot. And then we seek a linear, hopefully, our hope is that this is a linear transformation f, such that f does the thing that it should do if this is going to be translation, right? So that's what we did here. And we found through this process of what this should look like, right, algebraically, like what form this should take. If this is going to be represented by a matrix, the standard matrix really only has one form, which is the columns are what this f does to the basis vectors. It might not be immediately clear what it does to the basis vectors, like these two, for instance, based on the form that it takes. So we had to use some trickery, right? So in using our trickery here, we computed what it did to these vectors, and then used linear combinations of these vectors to obtain what it actually did to each of the standard basis vectors. So we computed what it did to 1, 0, 0. We found that that was the same. It actually fixed 1, 0, 0. It fixed the first standard basis vector. Similarly, it fixed the second standard basis vector in the same way. And we already knew that this third standard basis vector, it sent to AB1, right? That was one of the first things we computed here. And so, what that left us with was this matrix, which we then labeled T of AB, which we're calling our translation matrix by the vector AB. So this is a translation in 2D by this specified vector that has components A and B. And we checked that this actually does what we said that it does. So if we represent our point in the plane by xy1 and we multiply on the left by A, then exactly what we get is what we sought when we first wrote out what f should do if it is in fact a translation. Okay. So that is what we did. Now, I promised an example actually showing that this thing does what you think it does. So let's do this. Here's my matrix T of AB. So in the example that I'm going to do, let's just pick something here explicit. So let's translate. So translate by +2 in the x direction. And -5, and when we say +2, we mean, +2 units, whatever our units are, in the x direction, and -3 units in the y direction. i.e. translate by the vector 2 minus 3. So if you wrote this as a vector in the plane, 2 minus 3, right, this vector should look something like this. Here's my vector 2 minus 3. So that whatever this transformation does, it should take all of my points in the plane and shift them according to this vector, in the direction of this vector and in the length indicated by that vector. Okay, or the distance, which is the length of that vector. So according to this previous this previous notation, that this translation matrix T of AB, I'm calling, has this form. This means that T of 2 minus, I'm going to use minus 5 just to be, I wrote it as minus 3 here, but I'm going to use minus 5 here. Rewrite all these as minus 5 just to keep this in one-to-one correspondence with the actual example I'm doing in the text. So sorry, all this should be minus 5 instead of minus 3. So T of minus 5 here is what? This is the matrix 1, 0, 0, 0, 1, 0, 2, minus 5, 1. Okay. So, how does this translate the points? We'll say 7, 1. And minus 3, 0. Now, of course, you could compute these translations separately, right, on their own, but there's no reason to do that because you can actually put it in a single matrix, right? So, how would we do this? We put these points in a single matrix, but of course we have to translate using our trick here. Well, here I'm using a different meaning of the word translate, right? I do not mean to move its position. We need to take both of these points and put them in the form amenable to multiplication by this matrix using our trick here, which is put each of these as a column in a matrix. The column associated to 7, 1 is 7, 1, 1. The column associated to minus 3, 0 is minus 3, 0, 1. That's our matrix. Now, we could have, if we wanted to, done this for any number of points, right? We chose 2 points here, so that's what I'm going to stick with. And so if I want to see how this translation affects these 2 points, I can actually multiply this matrix by my matrix T 2 minus 5. Right? So I'm multiplying these 2 things. When I do that, what do I get? I get the vector. You could just check this yourself, right? 1, 0, 2 times 7, 1, 1. This is going to be 9 minus 1. I'm going to read row-wise. Minus 4, minus 5, and 1, 1. Notice that the structure of this matrix ensures that these 1s remain fixed, which is important for us because they are basically just placeholder slots, right? Because now we're going to say, well, what does this mean when I multiply this matrix by T2 minus 5? It means that the point here, corresponding to this first vector, after this translation goes to the point 9 minus 4, and this point, which is minus 3, 0, goes to the point minus 1, minus 5. So 7, 1 goes to 9 minus 4, and minus 3, 0 goes to minus 1, minus 5. Right? So check, right? Plot these if you like. Check that this makes sense. Of course, it will make sense if it looks like these 2 points have been shifted both in the same direction, the same distance, and that direction is the one specified by the vector 2 minus 5. Right? Okay. So going from 2D to 3D in this way is not, going from this, writing my matrix in this form and writing these vectors in this form back to the points is no problem at all, right? I can just read it off. Now you might say, well, okay, what about this translation in 3D? How does this work? Well, we'll get there, but actually there's nothing new. There's no new trick that we're going to use here. We're actually going to do the same thing, essentially, that we did here. Once you understand this trick in 2D, and really, right, our trick in 2D was kind of inspired by what we did in 1D. So once you've seen how this goes, it's easy to build this up, and it's kind of straightforward to see how this is all going to work. Okay, so now that we have handled translations, what about rotations in 2D? Okay. So here's, the gears are probably already turning in terms of how this works because you're familiar with a variety of tools at our disposal for dealing with rotations in a convenient way, right? And so, the thing that you have probably thought about immediately here, whenever you're talking about rotations in the plane, you know that a very convenient way of handling those is to not speak in rectangular coordinates, but rather use polar coordinates. All right, this is going to be a very convenient way of dealing with this. And so let's see how this works. For a generic point, I'm just going to put the point in the first quadrant, but obviously we don't need to worry about that. Suffice it to say, right, I don't have to explain too much to say, if I understand how rotations work counterclockwise, then figuring out how they work clockwise is not too hard, right? So we're just going to assume that all rotations are counterclockwise because the way that all of the quantities that you're used to and how they are defined assume that counterclockwise is the positively oriented thing, we'll say. Now, could we have developed these conventions in a way that clockwise was the positively oriented thing? Absolutely. We're not going to do that because that would go against the conventions established in every other math course you've had up until now. So, right, that's something only physicists do stuff like that, right? Where they use some convention that nobody else uses that results in some minus sign that's not there in other cases, right? You can blame physicists for that sort of thing. So here is our point, and let's say that we want to rotate this point counterclockwise to this point that we'll call x naught, y naught. That's what we want to do. Now, this point, of course, has associated with it an angle measurement measured from to the positive x-axis. So we'll call this angle alpha here. And to describe this rotation, right, I am going to rotate through some angle about a point, right? Because that's the thing about rotation, right? I don't just specify a direction that is a vector, right, that tells me the length of the translation and the direction I'm translating in, but also I need to know the angle, the direction. Technically, I need to know if it's clockwise or counterclockwise, right, in this case, but we're saying clockwise is the thing we're assuming, so clockwise it is. So I need to know the angle that I'm rotating through, and I need to know the point that I'm rotating about. So the way that I have this set up is that I'm rotating about the origin. Now the reason that I'm doing the origin first is, one, because that's what I have my polar coordinates set up, right, for, right? The polar coordinates are, the origin is a special point for polar coordinates, a distinguished point. And so it's natural, but you might immediately say, well, but if I'm going to do rotations, like I need to be able to rotate about any point. You might already think to yourself how, if we can figure out how to do it about the origin, we can actually figure out how to do it, period. And we can do that based on something we just finished doing, right? Now I'll let you think about that, or how we can go about rotating about any point, assuming we can rotate about the origin based on what we've already done. Okay, so I want to rotate this point to this point, counterclockwise about the origin. Okay, so how do I do that? Well, my starting thing here, right? I mentioned polar coordinates. So this point that I'm starting with has polar coordinates. Its polar coordinates are given by what? Well, x is the length of this segment, its distance to the origin, which of course I can compute as square root of the sum of the squares of this thing. So this is square root of x squared plus y squared, times cosine of this angle measured to the positive x-axis, which is alpha. And similarly, y is that same distance to the origin times sine of alpha. Okay. Well, if that is the case, these are the polar coordinates that define my point here. What about x naught? Well, the thing is that I'm actually, right, like how circles work, right? If you go back to, compass straight edge things, right? This rotation is not scaling this point out. It's not moving this point out. So actually this is fixed. This distance is fixed. So this has the same distance to the origin that this point has, right? And so this is still x squared plus y squared. But now this is cosine of the angle measured between this line, right, passing through this point in the origin, and the positive x-axis, which is theta plus alpha, or alpha plus theta. Well, I have a sum of angles inside the argument for cosine, so I wonder, right, what algebraic fact I'm going to use, from trigonometry to deal with this. Well, I have the cosine, angle, sum, and difference formulas, right? Maybe you don't remember them off the top of your head. That's okay. What is this thing? So this is unchanged, this distance, square root of x squared plus y squared, times, what is this? This is my cosine, angle, sum formula. So this would be cosine of alpha times cosine of theta minus sine alpha times sine theta. But using this previous boxed answer here, right? What can I say? Well, square root of x squared plus y squared times cosine of alpha, that's x. So this is x. And then square root of x squared plus y squared times sine alpha is y. So this has a much more convenient way of writing it, which is x cosine theta minus y sine theta. Okay. So that's a pretty convenient way of writing this. Now, what about y naught? Let's do a similar sort of thing. Y naught, using, again, polar coordinates. This distance is exactly the same, so square root of x squared plus y squared. Now times the sine of alpha plus theta. which by the angle sum formula for sine is square root of x squared plus y squared. Here's a chance to plug another course. If you ever want to really easily remember basically every trig formula ever, take a complex analysis course if you haven't already. So Math 463. Because once you see the proofs of these things using complex analysis, you'll never forget them. Because those are the easiest forms of those proofs. They are very, very fast, like one-line proofs, and they help you remember exactly how these things go. So what is this? This is sine alpha times cosine theta plus sine theta times cosine alpha, which, using this same simplification pattern here, right, this is going to be square root of x squared plus y squared times sine alpha is y. So this would be y cosine theta plus x sine theta. Okay. Which we might, just to keep the convention the same, so that the x is coming first, we might rewrite this as x sine theta plus y cosine theta, doing nothing but just reorganizing this because of this matrix we're about to put this in. And so I have solved for given polar coordinates in my initial point. I know what the polar coordinates should be of this point that gets rotated to. This is going to be the most convenient way of describing what's going on here. Doing this in rectangular coordinates is really, really nasty, so this is definitely like the best way of describing this. So now what this means is that I know exactly how to describe what this translation, or sorry, what this transformation, this rotation is going to do in terms of my f. So what do I seek? Right? I seek a linear f such that, again, remembering that I have to insert this 1 as an extra like placeholder slot so that all this works, although you might start to question yourself and say, well, you know, rotation about the origin absolutely fixes the origin, so I don't have to worry about it in that sense. But you might also think to yourself, well, you know, does rotation about other points fix the origin? Right? Is the origin fixed if you are rotating about the point -5, -5? Well, you know, I mean, sometimes, depending on the angle of rotation, but maybe not always, right? So the point here is that I want to keep this convention even if you can identify rotations that do in fact fix the origin. So, you know, for translations, if you were translating by any vector that was non-zero, you were going to move the origin. So it was more obvious that translations were a problem. But you see that some rotations could also be a problem. So it is still beneficial for us, or required even, for us to keep this convention that we're doing. So we're seeking a linear f such that f of this vector xy1 is, in fact, its x component goes to x cosine theta minus y sine theta. Its y goes to x sine theta plus y cosine theta. And this last entry is this placeholder here. And so let's think about what this says. I seek a linear f such that f does this. It sends this point, which is the point xy, to this point, which, going backwards, is the point x naught, y naught. All right, this first thing is x naught, and this is, maybe I'll write it here. And the rotation I'm doing is a rotation counterclockwise through angle theta about the point 0, 0, about the origin. So that is what this will describe. Now, when we say that we seek a linear f here, that means we are imposing the condition that there's really only one form this thing can take, and the form that that thing can take is the same as it always is. This matrix A, this standard matrix, would have to be what? Its columns would be determined by what this F does to the standard basis vectors of R3, which are your favorite IJK vectors. Okay. Well, we can actually see how this would behave if we focus on, we're going to do exactly what we did last time, which is the way this is described. It's clear how this is going to transform 0, 0, 1, but maybe not immediately clear how it's going to transform 1, 0, 0, and 0, 1, 0 because I don't have a 0 here, right? And so I know the things that are easier to compute, which is what does it do to the point 1, 0? Right? Well, that is moved to this point. How does a rotation counterclockwise, right, from positive x-axis theta, radians from positive x-axis about the origin, move the point 1, 0? It moves it to cosine theta, sine theta, right? This is, if you like, right, this is even the definition of cosine and sine, right? So, okay, what about the point 0, 1? How is that moved? Well, this is moved to minus sine theta, cosine theta 1. Right? Remember reference angles, right? I'm not going to draw the picture here, but you all know unit circle. Remember reference angles in unit circle and how this works, right? If you're confused about the switching here. The other, or the last thing, where does it move? The point 0, 0. Well, it doesn't move the point 0, 0. It actually fixes the origin. So it doesn't move it at all. It sends the point 0, 0 to the point 0, 0. We have this 1 in the last slot because that's our way of representing these points in 2D. Now, I need to figure out what this matrix A is. I don't directly have these things. I do have this one. I have the last one. I don't have these things, so I have to use linearity here to figure out these two things. So I'm using linearity here. If I do that, f of 1, 0, 0 is f of, just like last time, this is f of 1, 0, 1 minus 0, 0, 1, so that I can subtract off this last entry here. By linearity, this is f of 1, 0, 1, which we know what it is, minus f of 0, 0, 1, which we also know what it is, which is f of 1, 0, 1 is cosine theta, sine theta, and this last entry, 1 minus 1, is 0. Right? So I'm doing this in my head here. Okay, but you could here, right? What is this? This is cosine theta, sine theta 1 minus 0, 0, 1 there. Right? Now I wrote it out. So this is cosine theta, sine theta, and 0. Let's use linearity again for the second thing, right? F of 0, 1, 0. So using linearity again, we say, okay, this is f of 0, 1, 1 minus 0, 0, 1, which is f of 0, 1, 1, which we know, minus f of 0, 0, 1, which we also know. This, of course, is minus sine theta cosine theta 1 minus 0, 0, 1, so that I get minus sine theta cosine theta 0. And now I know what my matrix A is. A is f of 1, 0, 0 in the first column, f of 0, 1, 0 in the second column, and f of 0, 0, 1 in the last column. F of 0, 0, 1 is 0, 0, 1, fixes the point 0, 0. F of 1, 0, 0 is cosine theta sine theta 0. And f of 0, 1, 0 is minus sine theta cosine theta 0. So what is my matrix A? A here then is reading column-wise cosine theta sine theta 0 minus sine theta cosine theta 0, 0, 0, 1. Okay. This is my matrix. Maybe we will call this matrix R of theta to denote that this is rotating a point by angle theta counterclockwise about the point 0, 0, so about the origin. So this is the matrix that describes the transformation of any point in the plane so I'm doing a rotation counterclockwise about the origin through an angle of theta radians, right? So this is the description. Okay. Let's check that this actually works. So its general form. What if we apply r of theta to the vector xy1? Just remind ourselves what we want this to be, right? We want f of xy1 to be this thing, x cosine theta minus y sine theta, x sine theta plus y cosine theta, and 1. Let's check that that's actually what we get here. Well, r of theta, which is this matrix, times xy1, what is it in the first component? It is x cosine theta minus y sine theta. What is it in the second slot? This would be x sine theta plus y cosine theta. And in the last slot, it's 1. Hey, that's exactly what I wanted it to be, right? So this definitely does it. Okay, so this is our matrix that gets the job done. So let's do a very quick example here. Let's rotate the point. We'll say 5, 3 counterclockwise about the origin through an angle of pi over 6. So what is r of pi over 6 here? So first of all, what we would do here is we would have r of pi over 6 multiplying the vector 5, 3, 1. What is r of pi over 6? R of pi over 6 is going to be cosine of pi over 6. I'm going to read column-wise. This would be cosine of pi over 6, sine of pi over 6, 0. So this would be root 3 over 2, 1/2, 0. The next column would be minus 1/2 root 3 over 2, 0. The last column would be 0, 0, 1, times the vector 5, 3, 1, which would give us 5 root 3 minus 3 over 2 in the first slot. In the second slot, we would have 5 plus 3 root 3 over 2. And in the last slot, I would have 1. Maybe make this vector a little bigger. There we go. And you can check that if you plot the point 5 root 3 minus 3 over 2 and 5 plus 3 root 3 over 2 and compare these two, 0.53. To this point, you will see that it is the 0.53 rotated through an angle of pi over 6 counterclockwise about the origin. Okay. So that is how that works. All right. Now, here's the question, right? How do I combine these things? How do I combine these transformations? Well, there's if we remember back to what we actually defined when we were doing this, like one of the benefits of using matrix multiplication to begin with was that if we needed to think of a combination, right? A combination, concatenation, composition, whatever you want to call it, a combination of these transformations. So I do one transformation, then I do another, then I do another, then I do another in some specified order. The benefit of using matrix multiplication was that it was very easy to see how this worked, right? In fact, we had a way of doing it, right? Like if matrix A did transformation 1, and matrix B did transformation 2, and matrix C did transformation 3, and I start with an initial point x specified as a vector, then I do transformation 1 by multiplying on the left by A, then I multiply on the left again to do transformation 2, and then I multiply on the left again by C to do transformation 3. Because of generalized associativity property, there's no ambiguity here if I write these without parentheses, so I can just write it in this order. And I mentioned that, the thing to remember is that when you're doing it this way, yes, we do A, then B, then C, but of course, in terms of matrix multiplication, this would be reading from right to left, right? So it would be like this. So this is how we're going to combine these things. Okay. This is going to be useful, if you haven't figured out already, in seeing how to rotate, for instance, about other points, right? Points other than the origin. So let's do a quick example. Suppose that I wish to translate by the vector minus 2, 7. Remember, we can interpret this as translating in the x direction minus 2 units and by 7 units in the y direction. But this is really a single translation, so I don't want to phrase it like that. And then rotate counterclockwise. Again, I'm not going to specify this every time. When I say rotate, you can just assume that it's counterclockwise. And then rotate about the origin pi over 2 radians. Right? Okay. So what's the translation that I'm doing? The translation I'm doing is this thing, right? Which we know the form that that matrix takes, right? Reading column-wise, this is 1, 0, 0, 0, 1, 0, and then minus 2, 7, 1. And then our rotation matrix is R of pi over 2, which is just reminding ourselves here, again, reading column-wise, is cosine pi over 2, sine pi over 2, 0, minus sine pi over 2, cosine pi over 2, 0, 0, 0, 1, which very quickly here, right, this is 0, minus 1, 0, 1, 0, 0, 0, 0, 1. I know I was reading column-wise here and then row-wise there, so I did something bad, but it's fine. Okay. So then, if I'm looking for the matrix, right, the single matrix that does this exact combination of transformations, that is, translates the vector first and then rotates it, what matrix product am I looking at? I'm looking at the matrix product, which is, remember, the thing that happens last is furthest to the left. So it's this thing, which if you multiply this out, you will see that this matrix is, I'm reading row-wise here, 0, minus 1, minus 7, 1, 0, minus 2, and 0, 0, 1. Okay. So then, to take this thing and apply it to a point, right? So to apply this to the point 5, 3, of course, you are free to apply this to any number of points, right? You could put each point as a column vector in a matrix and do this multiplication in that way. I'm just going to do it to one point to show you how this works. So to apply this, I would take this matrix, which I'm still going to write as this matrix product, and I would apply it to the vector 5, 3, 1. And when I do that, you will see that what I get is minus 10, 3, 1. And you can ask yourself whether or not this makes sense. Okay. All right. So, I keep referring to this, but now it's time I actually write it out explicitly, I guess, which is, question, what about rotating about a point that is not the origin? So what do you do when you want to rotate about a point that's not the origin? So, for instance, let's say I have a point here. We'll call this Q. And then I have some other collection of points here, say P1, P2, and P3. And let's say I want to rotate about Q rather than the origin. What do I do to do this? Well, may have already figured out by just thinking about this. Okay. What I could do is there is, a unique vector that specifies, say, this here, right? I can draw in the vector. Imagine that's actually a straight line. I can draw in this vector here, that points from Q toward the origin. And I know what that vector is, right? For any given point Q, I know what that vector is. And so what I could do is I could actually shift this whole plane right? I could translate the entire plane so that after the translation, Q would sit here. So I'd translate Q to some Q prime, but that Q prime is actually just the origin. And it is going to move these points in the exact same fashion, right? So all of them are going to be translated exactly the same. I can move this to the origin. Now that it's at the origin, I know what rotation about the origin looks like. So I could do my rotation about that Q prime, right? Which is sitting where the origin is. So it's the origin, and I know what rotation about the origin is. So I do the rotation I want to do, and then once I'm done, I could shift back via a translation in the opposite direction, right? Same distance, same length, but opposite direction. Okay. Well, does this work? Is it going to take all of these points? Is that combination of transformations going to take all of these points to where they should go as if I was just rotating about Q in the first place? And the answer is yes. Okay. So, say I want to rotate counterclockwise, again, as always, pi over 6 radians about the 0.47. What do I actually do? I first translate from 4,7 to the origin. To do that, I translate by the vector -4, -7, right? I then do my rotation. I then translate back, which is translation just by the original vector itself. Which, if I were to multiply this out, the matrices in question would be, I'm going to read column-wise here. So this is 1, 0, 0, 0, 1, 0, 4, 7, 1. The rotation matrix for pi over 6 is cosine pi over 6, which I'm just going to write. So this is root 3 over 2, 1 half, 0, minus 1 half, root 3 over 2, 0, and then 0, 0, 1. And then the matrix for this would be 1, 0, 0, 0, 1, 0, minus 4, minus 7, 1. So it'd be that product of those three 3x3 matrices. And if you actually do this out, you will see that this is approximately, because I got these nasty, I got square root of 3 roaming around here. This is approximately, I'm going to read column-wise here, so this is a 0.866, 0.5, 0, minus 0.5, 0.866, 0, and 4.036 minus 1.062, and 1. Okay. And if I actually apply this thing to a point, say the 0.52, you can see for yourself that how would you apply it to 5,2, right? You would take that matrix, whatever this is, we'll call this matrix M, right? You would apply it to the vector 5, 2, 1. And what you would get is, in fact, 7.366, 3.17, and 1. Which you can check by plotting that this does the exact thing you want it to do. Okay, it is a rotation about the 0.47 counterclockwise pi over 6 radians. Okay. All right, so we have solved kind of the one lingering thing that we had, which is being able to talk about rotation about a generic point is important, and so we have done that. Now you might complain and say this is kind of a roundabout way of doing it, but this is a very straightforward in terms of computations like multiplying matrices. It's a pretty straightforward computation here. So even if it might seem tedious to get what we want out of it, this is still pretty nice and pretty low tech, right? So we have kind of papered over the last concern we might have had. Now, the big thing that you might have noticed is that I began this discussion talking specifically about 3D graphics, right? Say the graphics of some 3D game that you're playing on your PC, and we know that first of all we need to know how to do all these things in 3D, and then we need to know how to move from 3D to 2D in the sense of projection, because ultimately all this is going to be projected in a 2D sense onto your computer screen, onto your monitor, right? The screen you're using to actually look at this thing. And so, before we talk about projection, let's take the transformations that we have managed to cook up in the 2D case and just extend them, right? Just generalize them to 3D. So now I want to talk about translations and rotations in 3D. And I'm going to start with translations because they're easier to talk about. 3D rotations are actually pretty annoying. They're pretty tricky. So I'll leave those for a little bit later. There's also, when we talk about 3D rotations, there's kind of a nice, convenient way of doing this, which I'm not going to go too much into that direction because we don't need to for our purposes, but I'll at least mention it. Let's talk about translations first. Basic idea is the same. I represent a point xyz using the vector xyz1 for the exact same reason that I did this in 2D, right? Because translations in 3D also move the origin, therefore are on their face just not linear, right? They move the origin, which is bad for linearity. Okay. So then, based on this, what do I think translation by the vector that has components a, b, and c is going to look like? Well, I know what it's going to look like, right? Because the algebra works exactly the same. Just because we moved to 3D doesn't really change what's going on here, right? And so the only thing is now instead of having a 3x3 matrix, what am I doing? I have a 4x4 matrix. So what is this? Reading column-wise, this is 1, 0, 0, 0. This is 0, 1, 0, 0. This is 0, 0, 1, 0. And then lastly, A, B, C, 1. This is how translation by this vector works. Okay. Not much else to say there. Right, that's exactly how it works. You can check for yourself that this exactly does what you want it to do. What is it that you want it to do? You want it to shift this, right? T of A, B, C times the vector x, y, z, 1. What is that? You can just check yourself that this is x plus A, y plus B, z plus C, 1. Which is exactly the transformation that takes xyz and sends it to x plus a, y plus b, z plus c. Done. Okay. So translations are going to work like that. Rotations, however, are a lot trickier. These are tricky. Why are they tricky? Well, here, let's see. What do we got? Let's pick something. Let's pick something cool here. We pick a Jet Jaguar figure. Do we? Let's see here. Okay, let's pick an ancient deck box from days of yore. Okay, so here's an ancient deck box. Let's think about this just sitting in space here. And I'm going to describe how I can rotate it. Well, here's one way of doing it. All right, you can see the Jazam Jin on the back about to eat this guy or whatever. But is that the only way to rotate it? Well, no, of course not. I could rotate it like this. Oh, okay. I could also rotate it like this. I could also rotate it like this. Or like this. Or like this. So this is an annoying thing, right? Because you notice immediately that when we talk about rotations, so we rotate about, and if you're keeping track of dimensions, right? In 2D, our rotations are about a point, which is a zero-dimensional object, right? In 3D, what are your rotations about? Are they about a point? Well, there's really an axis of rotation. There's like a line of rotation here, which is a one-dimensional object. So this rotation that you're doing, right? So you have some thing here, some object. Maybe it's like some like cylinder or something, you know, like this. And how you're rotating it, like maybe you're rotating it with respect to this line, like, you know, maybe you're rotating it with respect to this line. Right, maybe you're rotating it like this with respect to this line. Here's like another rotation you could do. Right, so you're flipping it like this, maybe you're rotating it like that, flipping it like this. Like there's many axes of rotation. And for this reason, describing three-dimensional rotations is a lot trickier than even two-dimensional rotation. So here's where I come in with like the absolute, like most zoomed out theory and say, well, you know, all of these things technically, no matter how complicated they are to describe, that you could view all of them as one, two, or three reflections, right? But you know, notice we're not talking about reflections, even though, right? Like, you know, are there games that make use of a reflection mechanic so that it would actually make sense to incorporate reflection into these transformations? And the answer is yes, you could do that. You can actually do that. But when we're talking about computer graphics, you know, the things that are most relevant to us, of course, are translations and rotations. And it's simply not helpful that even though theoretically you might be able to describe them as a combination of different reflections about different lines or different planes, it's simply better to be able to directly describe them. So, you know, I mean, imagine trying to give like some like navigation data to some like spacecraft in terms of reflections instead of directly talking about the rotations involved. That's you know, that's kind of a funny thought experiment. But rotations in 3D. Probably the most convenient way of describing these involve the quaternions. We're not going to do this. But if you are interested in looking up what the quaternions are, constructed as, you know, what was kind of thought of at the time, constructed by Hamilton, I believe. What was kind of thought of at the time as a sort of pathological example for a particular type of what I'll call an algebra. There's also octonions, which are further generalizations of quaternions. But quaternions, it turns out, have a very nice interpretation that allows them to discuss 3D rotations very nicely. The relationships between the quaternions, which they have a variety of algebraic properties you're not used to in terms of how the algebra involving quaternions works. And so, if you're interested in this, you can look this up. I'm not going to go down this direction, but if you want to know like what a solution essentially is to describing these tricky 3D rotations, the quaternions provide a very nice way of doing this. You might think of them in the loosest sense as involving the I, J, and K that you know, although that's more of a we'll say that's more of a nice like superficial thing going on. And not entirely, but anyway, I'm going to stop talking about it, or we'll be talking about quaternions for the next hour or so, so I don't want to do that. All right, so what I will do instead is we are going to make some assumptions here. So idea. First, we talk about rotations, about the coordinate axes. Now, before I even finish this sentence, what I'm going to say is notice that in that example, there's not just an axis of rotation. I have to determine in what direction I'm spinning around, right? So here is where clockwise and counterclockwise simply do not suffice, right? Because there's too many directions. So you can't just say clockwise and counterclockwise. So then what is the analog of clockwise and counterclockwise? Well, you would say that with respect to these axes, I want the rotation to respect what we'll call the right-hand rule. So you saw me putting my right hand on camera earlier. But basically, if you remember how the right-hand rule goes for determining like directions, it is that you view the like positive axis as being your thumb sticking up out of the page or out of a board if you're writing on a blackboard or something. Thumb sticking up out of the page. The way that your fingers curl naturally indicate the direction of, say, the rotation you want to talk about. So, for instance, if we were talking about the XY plane here and I have the Z-axis coming straight up out of it, if my thumb is in the direction of the Z-axis, my fingers naturally curl, indicating a counterclockwise motion. So, the direction, for instance, in rotating about the Z-axis, looking down at the XY plane, using the right-hand rule would be counterclockwise rotation. So counterclockwise rotation about, say, the origin, for instance, would in this way respect the right-hand rule. So this is going to be our generalization of counterclockwise. So when we talk about rotations, we are going to assume that the direction of the rotation about this axis respects the right-hand rule. That will be the unwritten thing that we have in the background. And again, the reason for this is just like we did for counterclockwise. We don't want to have to continually try to specify these things. We're just going to assume this is the direction and leave it at that. Okay. The exercises in this section talk about like what happens if you change these things, how you have to alter things. So you don't worry about that. But for now, just to write some of this stuff down, this is what we're going to do. So we're going to say it respects the right-hand rule. Okay. So how are we going to do this? I already did the z-axis case, so let's do the z-axis case. The reason the z-axis case is natural to come first is, again, because imagine you have the xy plane here. Z-axis comes right up out of the page. How does this work, right? So this is the two-dimensional case. So if you We'll say here's our axes. Here's x, here's y, here's z. Viewed in another way, right? If here's my xy plane, the z-axis is coming straight up out of the page here. If I am looking at this in terms of right-hand rule, if positive z-axis is where my thumb is pointing, this is telling me how this rotation should work. So for instance, my finger's curling in this direction, thumb pointing in the direction of positive z-axis, indicates that this, if I'm looking straight down the xy plane, is a counterclockwise motion. That is, it is rotating the positive x-axis towards the positive y-axis. Okay, so in order for that to work in this way, what would my rotation about the z-axis theta radians look like? Well, it actually is going to look exactly like my normal rotation counterclockwise looks like. It's just I'm going to have like an extra row and column, right? So this would be, reading column-wise, this would be cosine theta, sine theta, 0, 0, minus sine theta, cosine theta, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now, you might just say, did you just come up with this based on vibes and how this felt? Or is there some reason why it works this way? The answer is, I mean, while you could have actually guessed the form that this had to take in a way, just kind of thinking about what the picture looks like, the main thing is like, what about this? Right, what's going on here? What's going on with this entry, right? Not just this column, but like this entry here. What is it that's happening? What is that saying about what this transformation is doing? Well, question I will ask you, and you can ponder it for a few seconds before I move on, which is, what's happening to the z-axis in this picture? Right? You can extend that to a question of what is happening to any axis of rotation when you do a rotation about that axis, right? So the answer is nothing. The axis of rotation is a fixed line. In fact, it is the only fixed line. Okay. If you're understanding what these transformations do in terms of the points that they fix, rotation is fixing. Rotation in 3D is fixing a whole line of points. That is the axis you are rotating about. So nothing happens to the z-axis, and that is indicated here. This is saying that the z-axis is fixed. Whatever is on the z-axis remains on the z-axis, no matter what theta is. Okay. This does the rotation that we want it to, and again, respecting the right-hand rule, because this is going to rotate positive x to the positive y here. Now, what about the x-axis? If we're careful here with how we're viewing this, thinking about the positive x-axis, we can actually more or less get what we want here by just swapping some things. So let's write out what the matrix for rotating about the x-axis is, again, respecting the right-hand rule. How would this look? So, what needs to happen? Well, the x-axis needs to be fixed now, right? So this first column needs to be 1, 0, 0, 0. And the reason why is because now the x-axis is being fixed. I'm rotating about the x-axis respecting the right-hand rule. Okay. Now the y-axis is taking the role of the x-axis in rotation about the z-axis. So the column here is 0 cosine theta sine theta 0. Why is this like, viewing this kind of superficially? Why is this here shifted down? Because y is playing the role of x in the z-axis picture, and z is playing the role of y here. So when we're rotating about the x-axis in this way, y is acting like x acted rotating about the z-axis, and z is acting like y acted rotating about the z-axis, which also immediately tells you what the z column has to look like, right? Which is 0 minus sine theta cosine theta 0. And then lastly, 0, 0, 0, 1. So that's what I meant by swapping the roles here, right? The rotating about the x-axis, respecting the right-hand rule, looking at how this behaved for rotating about the z-axis, respecting the right-hand rule. The only difference is here x and y play the roles they play. In rotating about the x-axis, y plays the role of x from before, and z plays the role of y from before, which is why this block matrix is located here in the middle. Okay, so now let's do a slightly trickier one, which is rotating about the y-axis now. Now you could say, what's special about the y-axis? Absolutely nothing. The reason why it's trickier is because it's the third one we've done after making sure the first two respected the right-hand rule. This, no matter what you start with, the third one is, if you start with the first one and pose the thing, going backward, the last one is always going to seem to be the odd one out. That's how it's going to work, right? So let's do the y-axis here. I want to put my sketch. I know it's not like the most detailed sketch ever. Maybe this doesn't help you at all, but there it is. I want to put it on this page. Now, what is the trick about rotating about the y-axis? We're obeying the right-hand rule. So what do I need to check? We didn't really check the x-axis. We were pretty confident of how this worked. But like, for instance, if we're respecting the right-hand rule, the positive y-axis should rotate towards the positive z-axis here, which is why y is playing the role of x. Okay, so here, now we are rotating about the y-axis. Here's positive y-axis, right-hand rule indicates a rotation like this, so that the positive z-axis needs to rotate towards the positive x-axis. That's what my right-hand rule is indicating here when I'm rotating about the y-axis. So this positive z-axis has to rotate toward the positive x-axis. And so what does this mean for this rotation matrix? Here, this means that z is playing the role of x and x is playing the role of y. Right? So what does this mean? How does this translate into a matrix here? So first of all, we know, we're rotating about the y-axis, we know that the y-axis needs to be fixed, so I know what the second column of this thing has to be. Right? I know the second column of this thing is 0, 1, 0, 0. And that's because the y-axis is fixed. The question is, what about this first column? So now z is, I've interchanged these roles, right, between x and z here. So this is still going to be a cosine theta, then 0, and then minus sine theta, and then 0, and then sine theta, 0, cosine theta, 0. Why the sign change here? Because of swapping the direction that this is happening in. Right? Z rotating towards the positive x-axis here. And then lastly, I know that the last column is what it needs to be here. And so that is what does it. Compare all of these, right? I don't know if I can fit them absolutely all on the page. Kind of, sort of. There we go. It's close enough. Okay, here, maybe if I fold this down here, here's our full description of all of these things. Okay, these matrices are my rotations about the x, y, and z axes uh, in a way that respects the right-hand rule. Okay, so this is going to allow me to build all of the rotations that I care to talk about. You'll see that in the exercise especially, this goes into how to handle rotations about a generic axis. But this is going to do it. This is going to get the job done. And so I think here's a good stopping point before we go on to the specifics of this stuff and then talk about projections, so that by the end of tomorrow's lecture, we'll be done with our discussion of computer graphics and we'll be on to the next topic. But I think this is a good stopping point, since now we've seen kind of the meat of what is going on, because now this is kind of the foundation of being able to do these transformations in 3D. Okay, so we'll see the specifics of how this works out next time. So I think I'm going to stop here, and I will see you all tomorrow.